Heat is quite literally everywhere. It drives absolutely everything around us, from massive planetary weather patterns to the engine in your very own car. But here's the wild part. It's completely invisible to the naked eye. We know it's there, we can definitely feel it, but how do we actually go about measuring it, especially in extreme thermal environments? Okay, let's dive into this because it's a massive question. How on earth do we measure this invisible flow of heat? And I'm talking about measuring it from the absolute subatomic quantum level all the way up to the kind of roaring macroscopic flames you'd see in heavy-duty fire resistance testing. Well, it turns out we have an incredibly diverse toolkit of thermal sensors at our disposal. And today, we're taking a journey from the micro to the macro world of thermal engineering. Here is our roadmap for the explainer today. 1. NQR atomic level thermometry. 2. Heat flux sensors explained. 3. The electrical circuit analogy. 4. Gardon versus Schmidt-Bolter. And 5. Advantages and limitations. Let's kick things off with section 1. NQR atomic level thermometry. We are zooming right into the quantum world. Let's start at the absolute smallest scale possible and look at how the nuclei of atoms themselves can actually act as tiny, unbelievably precise thermometers. So, what exactly is nuclear quadruple resonance, or NQR? Well, NQR uses radio frequency magnetic fields to induce and detect transitions between the sublevels of a nuclear ground state. Now, if you're at all familiar with NMR, nuclear magnetic resonance, this probably sounds pretty familiar, right? But here is the major game-changing difference. Well, NMR relies on a big applied static magnetic field to create that energy splitting. NQR relies on the interaction with electric field gradients that are already naturally present within the material itself. That means pure NQR requires absolutely no static magnetic fields to operate. By pinpointing specific nuclear transition frequencies, specialists can perfectly correlate those frequencies to the exact physical temperature of the sample. But here's the catch. You can't just pick any random atom for this. Nature has some pretty strict quantum rules. First off, the isotope has to have a nuclear spin greater than 1/2. That completely rules out common NMR isotopes like hydrogen-1 or carbon-13. Second, it needs a reasonably high isotopic abundance. Third, it has to sit in a solid with lower than tetragonal symmetry, which is basically a fancy way of saying the crystal structure isn't perfectly symmetrical in all directions. And most importantly, the nucleus must have a non-zero electric quadrupole moment. What does that actually mean? Well, it just means the nucleus isn't a perfect sphere. Think of it like a stretched out American football or maybe a squashed frisbee. When you hit all those quantum conditions, that uniquely shaped nucleus becomes a remarkably sensitive quantum thermometer. Moving right along to section 2, heat flux sensors explained. We're stepping up into the macroscopic world now. Leaving those static atomic temperatures behind, let's step into the dynamic macro world. Now, a heat flux sensor is fundamentally different from the standard thermometer you might have sitting outside your window. A regular thermometer measures the state of temperature, but a heat flux sensor, that is a transducer that generates an electrical signal perfectly proportional to the total heat rate applied to its surface. It measures the dynamic transfer of thermal energy, whether we're talking convection, conduction, or radiation, as it passes through a specific area. Basically, it tells you not just how hot a thing is, but how intensely that heat energy is actively moving. Now, what's really interesting about this is the math. It's beautifully simple, actually. To find the heat flux, which we represent here by phi sub q, you simply take the sensor's voltage output, V sub sen, and divide it by the specific calibration constant of that exact sensor, E sub sen. That's it. The result gives you the local heat flux density in one direction, usually expressed in watts per square meter. It is elegant, it's straightforward, and it's absolutely crucial for heavy engineering calculations. Let's actually peek inside one of these flat plate devices. If you follow the flow, heat moves from the hot side straight through to the cold side. The core of this thing relies on a filling material woven with two completely distinct types of metal wiring. In this specific setup, we're looking at constantan and copper. Together, these form a series of thermocouples, connected to create what we call a thermopile. As heat pushes through that filling material, it creates a temperature difference right across these junctions. And that difference self-generates the measurable voltage output we just talked about. It's brilliant. All right, section 3, the electrical circuit analogy. Let's make sense of these thermal dynamics. So how do engineers actually figure out how fast these sensors will react to, say, a sudden massive blast of heat? Well, they build a conceptual bridge. If you know a little bit about basic electronics, this brilliantly illustrates how heat flux sensor behavior maps perfectly onto a simple RC electrical circuit. Instead of electrical resistance and electrical capacitance, we just swap those out for thermal resistance, Rsen, and a thermal capacity, Csen, attributed directly to the sensor's filling material. By mapping complex thermodynamics straight onto simple electrical principles, we can easily predict exactly how this sensor is going to behave over time. And following that exact same electrical analogy, we arrive at this powerful little equation for the sensor's response time, or tau. This response time relies entirely on the physical properties of our filling material, its density, its specific heat capacity, and its thermal conductivity. But take a really close look at the variable d, which represents the sensor's thickness. Because it's d squared, a massive rule of thumb emerges here. The response time of your sensor is proportional to the thickness to the power of 2. Practically speaking, if you double the thickness of your sensor, it is going to take 4 times as long to react to a sudden change in heat. Which brings us to section 4, Garden versus Schmidt-Bolter gauges. Let's compare some real-world technologies. Now that we've got a handle on the physics and the math, let's look at the actual hardware used in intense real-world applications, like, for example, studying active fires. On one side, we have the inner workings of a garden gauge, which is also known as a circular foil gauge. It uses a very thin circular metal foil of constantan soldered right onto a copper heatsink. The heat hits the center, and it flows outward radially to the cooler edge, creating a radial temperature gradient. On the other side, the Schmidt-Bolter meter takes a totally different approach. It uses a relatively thick thermopile mounted directly on a heatsink. Here, the heat is conducted perfectly perpendicular to the absorber surface, straight down into the sink, which maintains a much more uniform temperature distribution across the whole surface. Because of these highly distinct designs, they naturally have different strengths. The garden gauge's circular foil construction means it absolutely has to measure convection perfectly perpendicular to its face to be accurate. But, and this is a big but, it can handle absolute extremes. We're talking heat fluxes up to an incredible 100 watts per square centimeter. To put that into perspective, that is basically like measuring the heat right next to the nozzle of a firing rocket engine. No joke. The Schmidt-Bolter gauge, on the other hand, tops out around 20 watts per square centimeter. However, its wire-wound geometry means it can accurately measure both perpendicular and parallel flows, making it highly versatile. Oh, and it's definitely worth noting that in crazy high-temperature scenarios, both of these sensors can be mounted on heavy-duty, water-cooled bodies just to keep them from melting. Finally, Section 5, Advantages and Limitations. Let's talk practical engineering. Look, no technology is perfect. Practical engineering is literally all about trade-offs. So the crucial point is, why do engineers love these thermopile-based sensors so much? Well, for starters, they offer incredibly high stability. They also have a very low ohmic value. This is fantastic because it means they pick up very little electromagnetic disturbance, which is absolutely perfect if you're working in a super noisy industrial environment. Add in a great signal-to-noise ratio and the beautifully simple fact that zero input literally gives you exactly zero output. But there is a catch. The main disadvantage you have to design around? Inherently low sensitivity. You are consciously trading away extreme sensitivity to get rock-solid, bulletproof stability. And wow, that brings our journey full circle. We have explored the invisible flow of heat by zooming all the way down to the quantum spin of a single nucleus in pure NQR thermometry, and then we zoomed all the way out to the water-cooled, heavy-duty macro world of Garden and Schmidt-Bolter heat flux sensors. Our physical world is entirely governed by these invisible thermal dynamics. So now that you know the mechanics from the micro to the macro, how will you apply these hidden measurements to shape the structural, mechanical, and safety designs of tomorrow? Thanks so much for joining me on this explainer today. Keep asking those big questions and keep learning.